Hi, my name is Molly Goldman, and today I'm going to be teaching you about heating and cooling curves. So let's just get right into a problem. The first problem that I'm going to show you says how many joules are given off when 120 grams of water are cooled from 25 degrees Celsius to negative 25 degrees Celsius. And on this slide, I'm just going to write all of the steps needed to complete this problem. So the first step is to draw and label a graph, and that's just going to really help you visualize information needed for the upcoming steps. Step 2, we're going to solve for Q1 and Q3 using MC delta T. And we're just going to do Q1 and Q3 because we're doing something different for Q2, which is step 3. So for step 3, we're going to solve for Q2 using stoichiometry. And then finally, step 4, we're going to add all 3 Q's together to get the final answer. So step 1, again, is just drawing and labeling a graph. So given information in the problem is that the water starts at positive 25 degrees Celsius and goes to negative 25 degrees Celsius. And we know that in between 25 and negative 25 is 0, which is the freezing point of water. So we just need to write that on the graph so that we know that there's a phase change going on. So then you can go ahead and draw your graph and label each part of the graph because it really helps you later. This is an extra step that I like to take. It really helps me sort out the information that I'm going to use later on in the problem. So what I do is I write what state each Q is in. So Q1 is in the liquid state because it hasn't been frozen yet. Q2 is obviously being frozen or freezing because it's at 0 degrees, which is the freezing point. And then Q3 just went through being frozen, so it is now a solid. And I just find writing these 3 things really helps me with step 2 and step 3. So then we're going to go on to step 2, which is solving for Q1 and Q3 using MCTF minus TI. So the first variable we need to find is the mass, which is given in the problem, so that's 120 grams. Then we just wrote down that Q1 is in a liquid state, so we look up at the graph and we see that the specific heat, or C, of water is 4.18. And then if we look on the graph that we just drew, we see the final temperature for Q1 is 0 degrees Celsius and the initial temperature is 25 degrees Celsius. When we plug that into our calculator, we're going to get negative 12,552 joules. We want to make sure to keep this in joules instead of converting to kilojoules because the problem does ask for joules given off, not kilojoules. So then we're going to go on to Q3, which is mass stays the same, is the only thing that stays the same in the equation, and that's 120 grams. So then we know that Q3 is a solid, so we're going to look up at the chart and see that the specific heat for water as a solid is 2.02. And then if we look at the final temperature of Q3, we get negative 25 degrees Celsius, and the initial temperature is 0 degrees Celsius. So when we plug that in, we're going to get negative 6,060 joules. Once again, we don't want to convert that since it asks for joules in the problem. So then we're just going to go on to step 3, which is solving for Q2 using basic stoichiometry. So we're going to start with what we're given, and we're just going to do stoichiometry to get this into kilojoules. So we're going to take the molar mass of H2O, which is 18 grams, which is equal to 1 mole of H2O, which is canceled out by 1 mole of H2O. And this is where it gets different. We looked on the chart, and we're now going to see that the heat of fusion for water, which is the same through all the states, is 6.01 kilojoules. So when we multiply this out in our calculator, we're going to get 40.066 repeating kilojoules. But we want to make sure that we're going to convert that to joules because the problem asks for it. I didn't write down the conversion, but when you convert it to joules, you're going to get 40,066 joules. So then we're just going to go ahead and do the final step, which is adding all 4 Q's together. So right now I'm just adding all 3 Q's together. I just added them all up, and as you can see, I did convert the last one into joules. And as my final answer, I got 22,048 joules given off. So for the next problem, I'm going to do one more with you, and this problem is just a little bit harder than the last problem because as you are going to see in about a minute, it does go through more phase changes than the previous problem. So this problem gives the same data as the last problem we were given. It's just not in the same format. And then the problem says, draw and label the heating curve for the following situation and answer the question. How much energy must be added or removed to change the temperature of a 730 gram sample of nickel from 350 degrees Celsius to 1,740 degrees Celsius. So once again, I'm just going to write all the steps down. It's pretty much the same steps as the last problem, just drawing and labeling the graph, and you want to make sure that you do that this time because the problem specifically asks for it. Then we're going to solve for Q1, Q3, and Q5 using MC delta T, and then we're going to solve for Q2 and Q4 using stoichiometry. And finally, we're going to add all 5 Q's together to get our final answer. So step 1 is just drawing and labeling the graph. Once again, we were given the information that the graph starts at 350 degrees Celsius and the nickel sample starts at 350 degrees Celsius and ends at 1,400 degrees Celsius. So if we look at the information given, we know that there's a melting point and a boiling point between those two temperatures. So we're going to want to put on the graph that the melting point is 650 degrees Celsius and the boiling point is 1,450 degrees Celsius. And then once again, you can just go ahead and draw all those phase changes and label each Q on the graph. So again, make sure to use, I already said this, but make sure you use the data above to find out when the nickel is changing phases. If you look above, it also gives the phase changes for water, but we aren't using water in this problem, so we don't need to use it. So once again, I'm just going to write the states of each Q. So Q1 is in a solid state, Q2 is the melting point, Q3 is the liquid state, Q4 is the boiling point, and Q5 is in a gas state. And once again, that's just going to help us know which data needs to go where. So we're going to continue on to step 2, which is finding Q1, Q3, and Q5 using MC delta T. So we're just going to go straight into Q1, which is the same thing as the last problem. We are given the mass of the nickel, which is 730 grams. And we know that Q1 is in the solid state because it hasn't melted yet. So we're going to look at the specific heat for nickel as a solid, which is 0.444. And then we're going to look at the graph and see that the final temperature for Q1 is 650 degrees Celsius, and the initial temperature is 350 degrees Celsius. So when we plug that into our calculator, we're going to get, you're actually going to get 97,236, but I went ahead and converted that to kilojoules because we need it in kilojoules for our answer. So going on to Q3, the mass stays the same, 730 grams. We know that Q3 is in the liquid state, so it's 0.75. Its specific heat is 0.75, and then we look on the graph and see that the temperature final of Q3 is 1,450 degrees Celsius, and the temperature initial is 650 degrees Celsius. So you're going to get 438,000, but I once again converted it to kilojoules, so you get 438. Going on to Q5, once again, the mass stays the same. We know that Q5 is in a gas, so we look at the data and get the specific heat, which is 1.05, and then we look at the graph and see that the final temperature is 1,750 degrees Celsius and the initial temperature is 1,450 degrees Celsius. When we plug that in, you're going to get 222,285 joules, but I converted it once again, so you get 222.285 kilojoules. So we're going to go on to step 3 of this problem. So that is solving for Q2 and Q4 using stoichiometry. This is basically the same concept as the last one. We're starting with what we were given in the problem, and we are converting it to kilojoules. We know since Q2 is we know that Q2 is melting, so that's the same thing as fusion. So the heat of fusion is 26.4 kilojoules. So we get 300, when you plug that into your calculator, you get 328.31 kilojoules. And then we're just going to go ahead and do the same thing for Q4. So we start with what we were given, 730, and we do the same thing, but instead of 26.4, we're going to use 62.6 kilojoules because Q4 is boiling, or the same thing as vaporization. So we look at the heat of vaporization, and that is 62.6 kilojoules. So for our answer, we're going to get 778.5 kilojoules. Then the final step, as we already know, is to add all 5 Qs together. So right here, I'm just adding them all together. Before you do this, you're going to want to make sure they're all in the same unit, so either kilojoules or joules. And then specifically for this problem, it asks you to write once you get that answer, it asks you to write if the answer, or if the energy needs to be added or subtracted from the nickel to get it to that temperature. And the answer would be to add this energy because you need to raise the temperature. So that's it for this problem and this video. I hope you learned from this video. Thank you for watching.